Hi everyone, this is Mrs. T, Mrs. T's Chem Talk for AP Chem. This video is for help with rice charts and equilibrium, but this is just going to be some help with getting some information on how to do those rice charts and how to use them with certain equilibrium questions. So in case you don't know who I am, my name is Mrs. T. I teach chemistry at Calhoun High School in Merrick, New York. And if this is the first time that you're watching one of my videos, or even if it's not the first time, if you want to just hit subscribe, this way you could find some access to all of my chemistry videos, both AP Chemistry and New York State Regents Chemistry. So you might get a question that might look like this, where it says, consider a reaction that are represented by this equation. Notice that usually you'll see a double-sided arrow. That means that our reaction is proceeding in both directions. That's usually the kind of arrow, something like that, is something that you will see when you're talking about a reaction that's going to have something to do with equilibrium. And in this particular question, it tells us that 6 molar concentration, iron 3 ions, aqueous, and 10 molar concentration of this SCN minus aqueous are mixed at certain temperature. And at equilibrium, the concentration of this iron ion here is 0.0050 molar. Okay, so since this question asks about the equilibrium constant, and since they give you initial concentrations and an equilibrium concentration for one of the species, we can use a rice chart or maybe what you call an ice chart in order to figure this out. And the rice chart is going to use the law of mass action in order to fill in and figure out mathematically the equilibrium concentrations of all the species. Because remember, once you have equilibrium concentrations, you have the ability to plug those into the K expression and then find the value of the K at that particular temperature. So for the first step, what we're going to do is we are going to set up a rice chart and we are going to write the K expression. So when I look at this reaction, remember that the K expression is going to be comprised of, oops, that's too thick, hold on, is going to be comprised of the products over the reactants raised to the power, that's better, of the coefficients. So for our purposes, iron 3 thiocyanate complex ion, which is that FeSCN2 plus, which is the product, that concentration, over the iron 3 concentration times, oops, sorry about that, the thiocyanate, which is that SCN minus. Now, because all of the coefficients were ones, the exponents in this case are also ones. Once we have our K expression, we're going to set up our rice chart. And our rice chart, rice stands for reaction, here's our reaction, initial concentration, change in concentration, and equilibrium concentration. So I'm going to go back and read the information from the question again, and it says that the initial concentration of the iron plus 3 ion was 6.00 molar. So I put that here in the initial concentration line. It also says that the initial concentration of the thiocyanate was 10 molar. Now I like to put a line down underneath the arrows because that separates my reactants from my products. And it says that these two substances or these two species were mixed, which means that we were putting them into a container where none of this complex ion existed at all. So the next thing after we fill in our initial concentrations would be to ask our Q question. Because remember, Q asks a question. And the question that Q asks is, are we at equilibrium yet? And if we're not at equilibrium, which way do we have to shift in order to reach equilibrium? So our Q is going to equal the initial concentrations of products and reactants plugged into the K expression. So for our purposes here, our Q equals 0 over 60, which is equal to 0. I put my Q and my K on a number line. We know that my Q is 0, and we know that K is some positive number, so it's bigger. K is bigger than Q. Anytime Q is less than K, we need to shift towards making products. If you put Q and K on a number line, whichever way you have to go to get towards K is the way that you will shift in order to reach equilibrium. So that means that my products are going to increase in the change and my reactants are going to decrease. Remember, whatever happens to the products is the opposite of what happens to the reactants. When I fill in my change line, I take the coefficients from the balanced equation and I put them in front of the x. We don't know how much they're changing by, but they all have a coefficient of 1, so they're all changing by an equal amount. I then read down and I combine my initial and my change to get my equilibrium amount. So at equilibrium, the concentration of this complex ion is X. At equilibrium, the concentration of thiocyanate is 10 minus X. I'm just getting rid of my significant figures here just for now, just for easier writing here. And down here I have, when I read it down, the equilibrium concentration of iron 3 is 6 minus X. And now if we go back and read the question, it said to us that at equilibrium, the concentration of our complex ion, the iron complex ion here, was 0.005. So that number is equal to X. And there was actually another 0 here, sorry. If that number is equal to X, I can plug that back in to each of these to find out the concentrations that they have at equilibrium. So at equilibrium, my concentration of iron 3 is 5.995 molar. My concentration of thiocyanate is 9.995 molar when I do my subtraction. So the next thing, once you have these values, these are the equilibrium values. And if you have your equilibrium values of your concentrations, well, those put into the equilibrium expression will give you the value for K. So I'm going to go and plug these in and say K equals 0.005, because that's where this one goes in the equilibrium expression, over 5.995 times 9.995. And that tells me that K equals 8.3 times 10 to the minus 5 at this temperature. So again, we wrote the balanced equation and we plugged in our reaction, initial, change, and equilibrium lines. We plugged in the given initial concentrations where it says initial. We asked the Q question and said, are we at equilibrium yet? If not, which way do we go to get there? When Q is less than K, and we knew that Q was less than K because Q was 0, K has to be a positive number. When Q is less than K, you shift towards making more products to reach equilibrium. That meant that our change line had to have a positive for the products and had to have a negative for the reactants. Then we plug in coefficient from the balanced equation, X, coefficient from the balanced equation, X, coefficient from the balanced equation, X. Because for every 1 mole of iron 3 and 1 mole of thiocyanate that are used, we get 1 mole of our complex ion over here. Our initial concentration combined with the change gives us the equilibrium concentration. And they told us in this problem that the equilibrium concentration of this ion was 0.0050 molar. That tells us that that's what X is. You can go back and plug your X into the E lines, the equilibrium concentration lines for your other species, and then use that information in your K expression. We know that equilibrium concentrations, when plugged into the K expression, will divide out to give us the equilibrium constant value. And remember that this K can be called K, it can be called Kc, or it can be called KEQ. Any of those designations would tell us that we'd be putting products over reactants and setting them equal to the power of the coefficients. Raising them to the power of the coefficients. So again, what did we do in order to complete that problem? We had to first write the K expression using the balanced equation. Remember, that was products over reactants to the power of the coefficients. The next thing that we did was that we made the Rice chart, reaction, initial, change, and equilibrium, and we filled in all the given information from the problem. Next, step 3 was to calculate the Q. Remember that Q asks a question. To reach equilibrium and say, is the product concentration increasing or were the reactant concentration increasing? Remember, since Q was less than the value of K, we had to make more products to reach equilibrium. In order to make more products, the concentration of the reactants had to decrease. Once we did that, we put plus coefficient X on the product side, and we put minus coefficient X on the reactant side. We read down the chart to combine the initial and the change lines, and when we combined those mathematically, we got the equilibrium concentration expressions in terms of X. We were able to solve for X because the equilibrium concentration of one of the species was given, and then we plugged those back into the K expression to find the value of K at that particular temperature. So we're going to do another practice problem here. And what I suggest, if you did the first one with me, what I suggest is that when you read this question, I would press pause here and see if you can do the steps. If you press pause here, you can always go back and rewind to the first question to see, or go back to the slide previously to see what the steps are to make sure that you're following them. And I recommend that you press pause and do a few of the steps. And then once you've finished the problem, you can watch the video to see if you did the right things, or you can press play to get some help. So I would suggest again that you press pause here and try to set this up before watching the solution. So at some temperature, hydrogen and nitrogen gas are mixed in a previously evacuated rigid container. The initial pressure of the nitrogen gas is 1.50 atmospheres. The initial pressure of the hydrogen gas is 3 atmospheres. Once the reaction reaches equilibrium, the pressure of the ammonia gas is 1.000 atmospheres. Find the value of Kp at this temperature. So before you press pause, I would just suggest that you notice that it says Kp. So instead of writing a Kc or a Keq expression, you are going to have to do this one in terms of pressures. So if you've already done some of this, hopefully you've done some of this and you're just checking back to try to get some help here, or to just check your answers. But once again, the very first thing that you're going to do is make sure you have a reaction written out. So nitrogen and hydrogen gas combining to make ammonia. Don't forget that nitrogen and hydrogen are both diatomics, and the formula for ammonia is NH3. You're going to set up your rice chart, and you are going to fill in any of the information that was given, as well as make sure that you write out your KP expression. So I'm going to do my KP expression over here. So remember, KP equals the pressure of the products, over the pressure of the reactants to the power of their coefficients. So it's the pressure of ammonia squared over the pressure of nitrogen times the pressure of hydrogen cubed. Whatever our equilibrium pressures are for the different substances, that will just get plugged into here to find the value of the Kp. The information that was given told us that the initial pressure of the nitrogen was 1.5 atmospheres. The original pressure of the hydrogen was 3 atmospheres, and since it was mixed in a previously evacuated cylinder, that means that there was no ammonia present. In reading the question, it tells us that at equilibrium, the pressure of the ammonia was 1 atmosphere. The first thing that we want to do before we put in our change is ask the question of Q, and we wind up with 0 over 1.5 times 3 cubed. So if Q equals 0, that automatically means that Q is less than K. We put them on the number line, and whichever way we have to move to get to K is the way that our reaction will shift in order to reach equilibrium. So since Q is less than K, we need to shift to make more products in order to reach equilibrium. So that means that my product side increases and my reactant side decreases. In my change line, it's always coefficient X, coefficient X, coefficient X. Because 1 mole of nitrogen combines with 3 moles of hydrogen to make 2 moles of ammonia. This is that law of mass action coming into play. For every 1 mole of nitrogen that is used, 3 moles of hydrogen are used. So the hydrogen will actually decrease in concentration 3 times as fast as the nitrogen. And ammonia will show up twice as fast as the nitrogen is consumed because of the fact that its coefficient is a 2. We will read down and say that the initial combined with the change gives us our equilibrium amount, and we were already told that at equilibrium the ammonia had a 1 atmosphere pressure. So that means that 2x equals 1 atmosphere. That means that x is 0.5 atmospheres. I'm going to go back and I'm going to plug that x into each of these sections so that I can find my equilibrium pressure of my other species. because remember, I want my equilibrium pressures, that's what the E in rice or ice stands for. I want my equilibrium pressures because my equilibrium pressures plugged into the Kp expression will give me the value of Kp at this particular temperature. So I wind up with Kp equals 1 squared over 1 for the N2 times 1.5 cubed. Ammonia squared over nitrogen times hydrogen cubed. And remember, these are equilibrium pressures. And when I plug that into the calculator, I get 0.296. So that means that at this particular temperature, the Kp is equal to 0.296. And that is also equal to the expression pressure of ammonia squared over pressure of nitrogen times pressure of hydrogen cubed. These are all one and the same. The Kp is this value, which at this temperature will always equal this expression when the situation is at equilibrium. So once again, in order to solve this problem, which was very similar to the first one, except it was in terms of pressure, we first wrote the K expression using the balanced equation. We then made the rice chart and filled in all the given information. We calculated Q. Remember that it asks a question. Anytime Q is 0, you're going in order to get to equilibrium because that would mean that Q is less than K. We then fill in the change line. Once you decide which side has to increase in concentration, you put plus coefficient on that, plus coefficient X on that side change, minus coefficient X on the other, because remember, in order to make products, you have to use reactants and vice versa. You read down to combine the initial and the change together, because the initial combined with the change gives you the equilibrium concentration. And the next thing you're going to do is use something to solve for X. I haven't done this in this video, but you might plug the terms in the equilibrium concentrations in terms of X into the K expression to find X. In this case, we found X and then plugged those equilibrium concentrations into the K expression to find K. Remember, E stands for equilibrium. Equilibrium concentrations plugged into the K expression will give you the value of K at that particular temperature. So this was Mrs. T's Chem Talk for AP Chem, information about how to rice for equilibrium. If you have any questions, any one of my students, please feel free to stop by Extra Help. If you're not one of my students, please feel free to search around on my channel and subscribe to do that. Search around on the channel, find maybe some other videos that you might find helpful. Have a good day. Happy studying.